Okay guys, a few more examples just to show some weird cases, some other things that you might come across as you're dealing with Lewis dot diagrams in the wild. Next example is going to be carbon dioxide, CO2. And so first up, determine the valence electrons. Carbon has 4, each oxygen has 6, and so that is a total of 16 valence electrons. We want to put the least electronegative atom in the center. Looking at a table between carbon and oxygen, oxygen is highly electronegative. It's usually going to be the most electronegative atom you have. Carbon is much less electronegative, and so the carbon is going to go in the middle of our CO2. So carbon in the middle, oxygen on one side, oxygen on the other side. Now we put pairs of electrons between all the atoms, so one pair between the carbon, one pair between the carbon and the oxygen on that side, and that's 4 of our electrons. We've got 16 more. So now we want to try and fill an octet, but we have 12 more. So currently the oxygen has 2, the carbon has 4, and this oxygen has 2 as well. So this oxygen needs 6 more, this oxygen needs 6 more, this oxygen needs 4 more. That's more electrons than we have. We only have 12, but if we keep single bonds, then we would need to have more electrons than the 12 that we have left and available to us. So I know already going into this molecule that the 12 electrons we have left after putting those 2 bonds in, that's not enough. For 6 more for one of the oxygens, 6 more for one of the oxygens, and 4 more for one of the carbons, the math doesn't work. So if we run out of electrons, we need to introduce multiple bonds. We typically start by keeping our molecules symmetrical. Whatever you do to one side, you do to the other. That's not a rule, though. There are molecules that are not symmetrical, and we'll see what's called a resonance structure here in one of our examples. But this molecule here, I put double bonds between each of the carbons and the oxygens, and so that uses up 8 total electrons. And so now, instead of having 12 left, we have 8 left. Let's check our octets. This carbon in the middle has 4 electrons here, 4 electrons here. That's a total of 8. Good, that octet is full. Now our oxygens, this oxygen has 4. That means it wants 4 more. This oxygen has 4, which means it wants 4 more. And we can count our electrons now. 2, 4, 6, 8, 10, 12, 14, 16. That's our 16 valence electrons. And so carbon dioxide looks like this. And that's the Lewis dot diagram for carbon dioxide, where I had to figure out that there were going to be multiple bonds between the atoms because we didn't have enough electrons to fill the octets. Next example. A bigger molecule. And I won't give you ones that are bigger than this typically, but I wanted to show you one where there isn't really a central molecule. So here we have C2H6. We know that the hydrogens can't go in the middle, and so the carbons are going to go in the middle. First, valence electrons though. Each hydrogen has 1, each carbon has 4, so that's 4, 8, and then plus 6 is 14. 14 valence electrons. And so on this one, I'm going to put my carbons in the middle, and I'm going to put the hydrogens all around them. Because so in this molecule, each carbon is bonded to 3 hydrogens and 1 carbon. And so to put the pairs of electrons between each of them, put a pair between the carbons, and then a pair between all of the hydrogens. And so counting our electrons now, 2, 4, 6, 8, 10, 12, 14. We've used them all. So hopefully we have full octets on all of our atoms. So each carbon has 8, good. Each hydrogen has 2, which is what it wants. And so this one has full octets. And so this molecule, which is ethane, looks like this. And that word I said to name the molecule was ethane. But that's nothing you'll need to know. That's an organic chemistry stuff. So that's beyond this class. I'm giving you extra knowledge because I think it's cool. That molecule is called ethane. Okay, final example, and it's one where we're going to see something interesting with it. So on all of these other ones, each molecule had one option, one structure that worked. NO2 has multiple structures that work. So here's why. So if we figure out the valence electrons, nitrogen has 5, oxygen each has 6, so 6 plus 6 is 12, plus 5 is 17. 17 valence electrons. And that's different from all of the others because all of the other examples we looked at had an even number of valence electrons. But when you start throwing nitrogen in the mix, we end up with an odd number of valence electrons, and that makes it, well, we're going to have an unpaired electron. In all of the other examples, our electrons have come in pairs, but not in this one. And so we start with the least electronegative atom in the middle. Between the two of them, nitrogen is less electronegative than oxygen. So N in the middle, oxygen's on the outside. And we start with a single bond between the two of them. And so that means that we now have 13 more valence electrons to use. That nitrogen currently has 4 valence electrons. It wants 8. We'll see what we can do about that. The oxygens have 2 each. They want 8 total. And so we're going to have to figure out what to do with those. So I start by putting some of my electrons. I'm going to put an electron pair on each of the oxygen. And so that's 4 more electrons. That means we're down to 9. So we have 9 more to place. But I know that I can't split that up evenly. Also, it's not going to be enough. The oxygens each need 4 more, but we only have 9 to give, and the nitrogen also needs 4 more. So it's sounding like we need to add a double bond. I'm only going to add one of them. So one of the nitrogens is one of the oxygens is double bonded to the nitrogen. The other oxygen is just single bonded. So total electrons right now, 2, 4, 6, 8, 10. So right now we have 7 electrons left. And so, again, an odd number. We keep placing them. So this oxygen now has 6. So it's getting closer to where it needs to be. Let's give it 2 more to give it a full 8. And so then the nitrogen now has 2, 4, 6. It needs 2 more, so I'll give it another pair. And then we count our electrons because I lost count. 2, 4, 6, 8, 10, 12, 14. We have 3 more. We put them on the oxygen over here. And we have a lone electron. You'll learn more about lone electron pairs in future chemistry classes, but for now, we just want to know that they're not very stable. Lone electrons, they don't like being alone. It's kind of like us in quarantine. It would be so much happier if there was someone else in this apartment. But we're lonely, and that electron is also lonely. And so this gives us what's called resonance. And resonance is where we have multiple structures that exist at the same time, or they flip-flop between them. Resonance, what exactly is happening in resonance is kind of hard to understand at this level, but what it means is there's essentially two possibilities for this molecule that exist at essentially the same time. We can have this one, or, and this is how we represent resonance structures, I'm using proper notation here, we can have this molecule. But Ms. Walker, those molecules are exactly the same. They're just mirror images of each other. Yes, you're absolutely right. They are exactly the same. Except, isn't this oxygen a different oxygen than this one? What if I labeled them somehow? What if they were different isotopes of each other? Then they wouldn't be the same molecule each time. They would be different molecules. Is it oxygen 1 that's double bonded to the nitrogen, or is it oxygen 2 that's double bonded to the nitrogen? And that's what resonance kind of captures. Because these two structures, since they can both exist, it means that that lone electron has a lot lower energy. It's stabilized, essentially. And so it adds stability to the molecule to have resonance structures. And that's how to draw Lewis dot diagrams. I'm going to have other instructional videos from Khan Academy and other places in case this wasn't making sense or you feel like you're missing just a little piece in your understanding. On Wednesday, we will go over questions on this. We can go over questions on this on Monday as well. Hit me up on Remind or email, and we'll figure it out. This is really the last new stuff that we're learning for our test here, but this is what we want to get through, and then we can be done with bonding for a while. All right. Stay tuned for the next video. I'll see you next time.